Section 2.6, rational functions and their graphs. So our objectives for this section are to first find the domains of rational functions, to use arrow notation, which is also going to lead right into limit notation, to identify vertical asymptotes, to identify horizontal asymptotes, to use transformations to graph a few rational functions, to graph the rest of the rational functions, to identify slant asymptotes, and to solve applied problems involving rational functions. So if we remember what a rational function actually is, it's a rational function is a quotient of polynomial functions. So when we have a rational function, we are going to have one function divided by a second function. Okay? So when we looked at the graph of polynomial functions, we had a few techniques about how to graph it. We talked about symmetry, we talked about end behavior, we talked about turning points, we talked about finding where the graph crosses the x-axis, using multiplicity to figure out whether the graph goes straight through the axis or turns around at that point. The techniques for rational functions are going to be slightly different. Okay? So while those techniques are great for a polynomial function, for rational functions, they're going to be a little bit different. And we need to recognize a rational function as something divided by something else. One function divided by a different function. Okay, so let's look at the rest of this. So a rational function can be expressed as f of x is equal to p of x over q of x, where p and q are both polynomial functions. Q of x cannot equal to 0, of course, because the denominator of a function can never be equal to 0. The domain of this rational function is the set of all real numbers except the x values that make the denominator equal to 0. And we saw this when we were solving rational equations. Okay? Remember, we had to have those excluded values, which were things that make the denominator equal to 0. So the domain of a rational function is every real number except for all the things that make the denominator equal to 0. So if we look at this function right here, the top is p of x, the bottom is q of x, and this function is defined everywhere except for the three places that make the denominator equal to 0. 0, 2, and negative 5. Okay? So with each one of those, in each one of those cases, something is happening at those points. The function is not defined there, and we're going to see what that means in a little bit. Okay? So first, find the domain of each rational function. Okay? So, and we're going to write the domain in two ways. We're going to use our set builder notation, and we're going to use interval notation. Okay? So the domain here, well, first I need to factor the denominator. It is factored. Okay? So we set it equal to 0, and we see that x is equal to 3. That means the domain of this function is everything except for 3. So if I want to write that in set builder notation, I could write it as x such that x is not equal to 3. And we can assume that x is a real number, so I don't have to write it. Or we can say that the domain in interval notation goes from negative infinity to 3, is not equal to 3, and goes from 3 to positive infinity. Okay? Let's look at a few more. Okay. So the first thing I have to do is factor the denominator. So we have x over, factoring x squared minus 9 gives me x plus 3, x minus 3, which means that x cannot be equal to plus or minus 3. Okay? So the way I write that as a set builder notation, that we have a variable x such that x is not equal to 3 and x is not equal to negative 3. Or with interval notation, I go from negative infinity to negative 3. I go from negative 3 to positive 3, not including these points, and then from 3 to infinity. Let's look at one more. Well, the bottom here, it doesn't factor with real numbers. If I set it equal to 0, you'll see that when I take the square root of both sides, we get plus or minus 3i. Okay, well, because this is imaginary numbers, because there is no real number that makes the denominator equal to 0, this function is defined for all real numbers. So the domain here is all real numbers, or the domain here is from negative infinity to positive infinity. Terrible infinities. Okay. Uh, let's do some checkpoint problems. So here, my domain here, I'm just going to jump right to interval notation, right? Everything but 5. So we go from negative infinity to 5, and from 5 to positive infinity. Here, factor that, that's plus or minus 5. So we go, we're going to need a little bit more room for this, from negative infinity to negative 5, from negative 5 to positive 5. Oh, need a union. And from 5 to positive infinity. That's the domain of this function right here, function b, because when I factor the bottom, I get x plus 5, x minus 5. And here, just like the last example above, that does not factor into real numbers. The domain here is from negative infinity to positive infinity. Okay. Okay. This function should be familiar. We talked a little bit about it at the beginning of this chapter when we were doing transformations and parent functions. This is the parent reciprocal function. Okay, so you should remember that it's defined in 2 quadrants. It happens to be an odd function because if you reverse it, we get the opposite. Right? If we spin it around 0, it's reflected about 0. And there's a couple other things that are important about the reciprocal function that we're going to talk about right now. So one of the most basic rational functions is called the reciprocal function, defined by f of x is equal to 1 over x. The denominator of the reciprocal function is 0 when x is equal to 0. So the domain of f is the set of all real numbers except for 0. Makes sense, right? If we set the denominator equal to 0, okay, this function is not defined. So this function is defined for everything except for 0. So let's look at the behavior of f near the excluded value of 0. We start by evaluating f of x to the left. So if I were to plug negative 1, remember here's my function. If I were to plug negative 1 into this function, I would get negative 1. If I were to plug in negative 1/2 into this function, I would get negative 2. If I plugged in negative 0.1, I would get 10, and so on and so on. So you can see that as my numbers are getting smaller and smaller and smaller, these numbers are getting larger and larger and larger. And in fact, they're getting a lot larger. Okay? And you can see that we are going approaching 0 from the left. We're starting at the left. We're starting over here, right? And we're going closer and closer to 0. Okay? Mathematically, we say that as x approaches 0 from the left, from the table and accompanying the graph, it appears that as x approaches 0 from the left, the function values f of x decrease without bound, right? They're going down. They're getting much, much, much smaller, okay? We can use arrow notation and limit notation to describe this situation symbolically. So as x approaches 0, and this little negative right there means that you're approaching 0 from the left, because different things can happen in a function as you approach a number from one side or the other side. So you think about starting to the left of 0 and moving closer and closer and closer to 0. That's what this symbol right here means, this little negative sign. Okay? So as x approaches 0 from the left, the function, the answers, get much, much, much smaller. F of x approaches negative infinity. So these arrows mean approach, right? It tells you where you're going. These things tell you what you're going towards. So observe that the minus superscript on the 0 is read from the left, not 0 negative power. Okay, we read it as x approaches 0 from the left. Okay. Another way to think about this as this is arrow notation. So this arrow notation, we can smush it kind of together, and what we get is something called limit notation. So all the limit is what's happening as you get closer and closer to a number. Well, as x gets closer and closer to 0 from the left, the function equals negative infinity. And that's all the limit is. So we can say the limit as x approaches 0 from the left of my function, which happens to be 1 over x, is equal to negative infinity. So basically all limit notation does is it combines this arrow notation and puts it together into one thing. Okay? This is good. This is a little better. Okay? Let's look at the other way. So as x approaches 0 from the right. So as I plug in into my function, right? Remember, here is my function. As I plug in 1, I get 1. As I plug in 0.5, I get 2, and bigger and bigger and bigger. So as we approach 0 from the right-hand side, as we start over here, and we go this way, closer and closer and closer to 0, these numbers are getting bigger and bigger and bigger and bigger, which means they're going up towards positive infinity. So mathematically, we say that x approaches 0 from the right, and from the table and the accompanying graph, it appears that as x approaches 0 from the right, the function values, f of x, increase without bound. So we say that f of x approaches infinity. So as we get closer and closer to 0 from the right, the numbers get larger and larger and larger. With arrow notation, I have my notation here that says as x approaches 0 from the right, f of x approaches infinity. Okay? The plus superscript means from the right. With limit notation, the way I would write it is the limit as x approaches 0 from the right of my function is equal to infinity. Okay? And remember, that is the function that I'm talking about. Okay? I could have just put f of x, okay? But we are talking about a specific function here, so we can use the actual function. Now let's see what happens to the function values of my reciprocal function, f of x is equal to 1 over x, as x gets further and further away from the origin. So if you look at what happens, if I start plugging numbers that are bigger and bigger and bigger into this function, into the denominator here, notice that my answers get very small. And notice here that my answers get very small. So what's happening at the ends of this function is that they are getting progressively closer to 0. This number is very close to 0, as is this. And they're getting closer and closer to 0 as you go further away from the origin. So what that means we can do with arrow notation is say, well, this illustrates the end behavior as x increases or decreases without bound. The graph shows that the function values f of x are approaching 0. And this means that x increases or decreases without bound. The graph of f is approaching the horizontal line y is equal to 0, the x-axis. We can use arrow notation to describe this situation. As x approaches infinity, the function approaches 0. As x approaches negative infinity, the function approaches 0. Okay? Thus, as x approaches infinity, or as x approaches negative infinity, the function values are both approaching 0. And the way I would write this with limit notation is the limit as x approaches infinity of my function is 0, and the limit as x approaches negative infinity of my function is also 0. Okay? So limits simply are just what the graph is getting closer and closer to as you get to a specific point. Okay? So the arrow notation used throughout our discussion of the reciprocal function is summarized in this following box. So the symbol as x approaches a from the right, this means as x approaches a from the left, as x approaches infinity, as x approaches negative infinity. Okay? Just don't get confused with these two symbols, which means that this one says if here's a, you're going to start on the right and you're going to get closer this way. This one means you're going to start on the left side of a, which could still be here, and get closer and closer to it that way. Okay? So you're just going to start somewhere to the right of that thing, of that value, could be anywhere, it doesn't matter, and get closer and closer to it. And of course, another basic rational function is 1 over x squared. The graph of this even function, right, because x squared is an even function, because if I were to plug negative x into the function, right, it would still give me my original function. That means it's even, which means it has y-axis symmetry, and positive function values is shown in my figure right here. Like the reciprocal function, the graph has a break and is composed of two distinct branches, only the two branches happen to be both in a positive quadrant or a negative quadrant. And now we can see that we can talk a little bit more about this limit notations. And in calculus, you will use limits to convey a function's end behavior or possible asymptotic behavior. We can use limit notation to express the end behavior to the right. So the limit as x approaches infinity is 0, because I can see it's getting closer and closer there. And also the limit as x approaches negative infinity of this function is also 0. We could also say that the limit as x approaches 0 from the right of my function, well, I'm going to start at the right, and as I get closer and closer to 0, this function gets closer and closer to positive infinity. And as I approach 0 from the left, it's also positive infinity as well. Okay? So let's spend a quick second here to make sure we understand this particular function. I know with the graph, it's pretty simple because I don't have to plug any numbers in. This says the limit as x approaches negative 5 from the right. So we're going to start over here. We're going to get closer and closer and closer to negative 5, which is an asymptote. Okay, so that means the graph, where does the graph go? Well, it starts going up towards infinity. The limit as x approaches negative 3 from the left. Well, where's negative 3? It's right there. I'm going to approach it from the left side of negative 3, and you can see as you get closer and closer to negative 3, the graph goes up. Okay, right? We can also look at other situations on this particular graph. The limit as x approaches positive 3 from the left, I don't want to write this whole function, of my function is equal to, well, we want to go to the left of negative, we want to go to the left of 3. As we approach there, the graph goes straight down, so that would be negative infinity. Okay. And the limit as x approaches infinity is going to be 0, and as x approaches negative infinity is going to be 0 as well, because the ends of these graphs are approaching the x-axis. Okay, so hopefully you see kind of how limit notation works, and let's get into figuring out how these things work right here. Vertical asymptotes of rational functions. So if we look again at the graph of f of x is equal to 1 over x squared in my figure, the curve approaches but does not touch the x-axis. No matter how much I expand this graph, it will never touch that dotted line. It is said that the y-axis, or x is equal to 0, is a vertical asymptote of the graph. A rational function may have no vertical asymptotes, one vertical asymptote, or several vertical asymptotes. You can have as many as you want. The graph of a rational function never intersects a vertical asymptote, and we will use dashed lines on the graph to represent them. Okay, it's always a good idea now and when we graph trigonometric functions to use dashed lines to make vertical asymptotes, because it shows your reader, it shows whoever's looking at your graph that that is something that the graph never crosses. So the line x is equal to a is a vertical asymptote of the graph of a function f if f of x increases or decreases without bound as you get closer to that line. So with all vertical asymptotes, the graph is either going to go straight up or straight down. Okay? So you can see it in both my arrow notation and limit notation as we look at these graphs. This particular function, as we approach a from the right, the graph goes straight up. Right? So the limit as x approaches a from the right of f of x is infinity. Here, the limit as we approach a from the left is infinity. Here, the limit as we approach a from the right is negative infinity. And here, the limit as we approach a from the left is negative infinity. Okay? So in all of these cases, as we are going closer and closer and closer to these vertical asymptotes, the graph is going straight up or straight down. If the graph of a rational function has vertical asymptotes, they can be located by the following theorem. If f of x is equal to p of x over q of x, and it's a rational function in which p of x and q of x have no common factors, that's important, and a happens to be a 0 of q of x, so you figure out all the places where the denominator is equal to 0. Then x equals a is a vertical asymptote. So if you can find all the zeros of the denominator, then you can figure out all the vertical asymptotes. Okay? So let's find the vertical asymptotes. So here, the first thing I should do is factor. So that's x plus 3, x minus 3. Okay, so just like I'm finding the domain, this function is defined everywhere except for x is equal to 3 and negative 3, which means if I was to, well, first I look to see if it has any common factors, and it doesn't. So if I were to graph this function, I would expect there to be a vertical asymptote at negative 3 and at positive 3. And here's my graph. We have my vertical asymptote at 3 and at negative 3. Okay. Now here, when I factor this, I notice something. I notice that there is a common factor, which means when I cancel this out, I'm left with a new function that looks like this. So that means that negative 3, this 0 right there, is not a vertical asymptote. In fact, it is something else. When we have something that cancels, okay, we'll talk about this in a little bit, in a few minutes, it becomes something called a hole in the function, or a removable discontinuity. Because look what we did. We removed it, okay? Another name for vertical asymptotes is infinite discontinuities, because at the discontinuity, the function is either going straight up or straight down, right? They're going to infinity or negative infinity. So another name for the vertical asymptotes there are infinite discontinuities. Another name for these removable discontinuities are called holes, because when I graph the function, I see my infinite discontinuity, my vertical asymptote right here at 3, but right there, all I have is a space in the function that it is undefined. Because if I look at the original function, I still can't plug -3 into this original function without getting it to be undefined. Okay, but because I was able to cancel this discontinuity out, because I was able to cancel that factor out, right, it's not a vertical discontinuity. It's something like this called a hole. Okay, and with this one, clearly you can see that, like our other example before, there is no place that the denominator here is equal to 0. No real numbers make the denominator equal to 0, so the function has no vertical asymptotes. It happens to be a smooth function, okay, with a continuous function. Okay. Find the vertical asymptotes. So here, the vertical asymptotes would be x is equal to plus or minus 1, right? If I set that equal to 0, factor it, right? X over x plus 1 and x minus 1, okay? Here, notice we have x minus 1 over factoring the bottom, x plus 1, x minus 1. Those cancel. My only vertical discontinuity is -1, or my only vertical asymptote is -1. Positive 1, this one that canceled out, x equal positive 1, is a hole in the function, a removable discontinuity. And this one has no vertical asymptotes. Okay? So, more on holes here. A value which the denominator of a rational function is 0 does not necessarily result in a vertical asymptote. There is a hole corresponding to x equals a and not a vertical asymptote in the graph of a rational function under the following conditions. The value of a causes the denominator to be 0, but there is a reduced form of the function's equation in which a does not cause the denominator to be equal to 0. Basically, all that means is you can cancel it out. Okay, so if I look at this rational function right here, you would think that this would be a weird picture, a weird graph, but it's not, because if we factor the top, x plus 2, x minus 2, over x minus 2, we can see the x minus 2's cancel, and we're left with a graph that looks like this, x plus 2. Well, the graph of x plus 2 is pretty simple to graph, right? I didn't put it. It's just a line. Okay, so if I were to draw this, okay, well, right, we have x plus 2, which means that the slope is 1, the y-intercept is 2, so I know how to graph a function that looks like that. It's just a line. The trick is, at x is equal to 2, okay, at this point right here, instead of putting a dot, I would put a hole in the function. So this is what my graph looks like. It looks like a normal line, except for this one place where there's a break in the function. And this function is still not continuous because technically you have to lift up your pen to make that circle, right? This graph, you cannot make this graph by continuously drawing a line. And it is called a hole, or again, a removable discontinuity, because I was able to cancel it out. I was able to remove it. Okay. That's vertical asymptotes. Next is horizontal asymptotes. So here is my graph of the reciprocal function. As x approaches infinity and as x approaches negative infinity, the function values are both approaching 0. F of x approaches 0. The line y is equal to 0, the x-axis, is something called a horizontal asymptote. This graph the ends of this graph get closer and closer and closer to that line as you go further and further it out. Many, but not all rational functions have horizontal asymptotes. So, what do horizontal asymptotes look like? So instead of the graph, this blue graph, approaching a specific point, it's going to be, we're going to focus on the end behavior. So as x approaches infinity, the function approaches some number b. As x approaches infinity, this function approaches b. And notice here that the graph actually crossed the horizontal asymptote. But that's not what's important. The important thing is what's happening at the end of this function. Okay, so the line y is equal to b is a horizontal asymptote of the graph of the function f if f approaches b as x increases or decreases without bound. Recall that a rational function may have several vertical asymptotes. By contrast, it can have at most one horizontal asymptote. And although the graph can never intersect a vertical asymptote, it may cross its horizontal asymptote. The graph of a rational function has a horizontal asymptote. You can figure it out with the following theorem. So let f be the rational function given by f of x is equal to, and this is just the long way of writing a polynomial equation. This is the long way of writing a different polynomial equation, okay, with different coefficients but the same variable, okay. The reason why we have to write it out instead of writing p of x over q of x is because we're going to care about these numbers right there, okay. So we need to be more specific with our polynomial. And what you're going to do is you're going to look at the leading coefficients, the leading terms, okay. So the degree of the numerator is the biggest exponent here, which is this one. The degree of the denominator is the biggest exponent, which is that one. Okay, so what you're going to do is you're going to look at those two things. If n is less than m, if this one is less than this one, that means that there is a horizontal asymptote, and it is the x-axis. Y is equal to 0. Okay? Only if the bottom one is bigger. If the bottom exponent is bigger, the horizontal asymptote is 0. If they are the same, if the degree is the same, then the horizontal asymptote is a sub n divided by b sub m. These two numbers, whatever they happen to be, divided by each other. That's the horizontal asymptote. If the top one is bigger, there is not a horizontal asymptote. There is something different. And we'll get to that at the end of this section. So, do you have to factor to identify a rational function's possible vertical asymptotes and holes? Yes. Of course. You must factor to see what cancels and to find the zeros of the function. Do you have to factor to identify a rational function's possible horizontal asymptote? No, because we want to compare the leading coefficients, and it's harder to do when it's factored as opposed to easier. So, find the horizontal asymptote if there is one on the graph of each rational function. So all I do is I compare these two numbers. The top has 4x to the first power. The bottom has 2x squared. The degree of the top is 1. The degree of the bottom is 2. That means the degree of the bottom is 0. So the horizontal asymptote is y is equal to 0, the x-axis. And I can see that on the graph of this function. And the graph does happen to cross the horizontal asymptote, which is okay. It is not okay to cross a vertical asymptote. It is okay to cross a horizontal asymptote. What the asymptote is telling you is what is happening at the ends of this function. The limit as x approaches infinity of this function is 0. Because as this goes further and further and further out, it's going to get closer and closer and closer and closer to 0. Likewise, the limit of this function as x approaches negative infinity is 0 as well. This function. Now we look at these two numbers and we see that they are the same, which means we take the two leading coefficients, 4 over 2, which gives me 2, which means that this function has a horizontal asymptote at, if I can get this, there it is, at 2. So you see this function gets closer and closer and closer to 2 as you get closer and closer and closer to infinity. Okay? And notice that there's no place that makes this function, the denominator, equal to 0, so there's no vertical asymptotes. Same with this one. There's no vertical asymptotes because there's nowhere that this function is undefined on the denominator. Now, the top is now bigger, which means that we don't have a vertical asymptote or horizontal asymptote. But look at the graph. Notice that as we go towards infinity on the top and as we go towards infinity at the bottom, it doesn't look like they're approaching the same number, and they're not, but they do have something in common, is that they are getting closer and closer and closer to a diagonal line that looks kind of like that, which means that as the top gets bigger and bigger and bigger, we are going to have something called a slant asymptote. And we'll come back to that at the end. But the important part for this question is that there is no horizontal asymptote. There is no horizontal line that this graph gets closer and closer to at the ends. Okay. Horizontal asymptote. Here, it would be 3 because these two are the same. 9 divided by 3 is 3. Here, it would be 0 because the denominator is bigger. And here, there is no horizontal asymptote, but there is a linear asymptote, a slant asymptote, because this degree is 1 bigger. And again, we'll come back to that in a few minutes. So, what are we going to do with all this information? Okay. So basically what we're going to do is we are going to now graph rational functions. Okay. These two are easier. Okay. These two rational functions, we can use our transformations, right? Shift, up, down, left, right, stretch, reflect, all that sort of stuff. If we have a function that looks to be in one of these two forms, it has a 1 on the top or a number on the top, and then some sort of addition or subtraction or something like that, we can use our transformations, right? So to do that, we need to, of course, know what these two functions look like. So the basic rational function you should kind of know already, all right? And 1 over x squared, we can kind of figure that out pretty easily, okay? This one has a vertical asymptote at 0, a horizontal asymptote at 0. This one just has a vertical asymptote at 0, okay? This one is odd, and it has origin symmetry. This one's even, and it has y-axis symmetry. So, and we've done this a little bit before, I can use my basic transformations of this function to graph this thing, because if we remember, the parent function has been shifted 2 to the right and 1 up. So if I look at the parent function, I see that it has a horizontal, sorry, it does have both. It has a horizontal asymptote at 0. It has a vertical asymptote at 0. Now, instead, it will have a horizontal asymptote at, if I shift this 2 to the right, whoops, if I shift this 2 to the right, it's going to have a horizontal asymptote at 2. And if I shift it 1 up, it's going to have a vertical asymptote at 1. And you should get into the habit of drawing vertical and horizontal asymptotes with dotted lines. It will definitely help you. Okay, so if I look at my parent function again, this had a point of 1, 1. So my point of 1, 1, I can simply shift that right 2 up 1. Okay, and reflect it across, because it's even symmetry, and its symmetry now is going to be this line right here. Okay, we can also take the other points of the parent function, like this one. If I went right 1 from this point, or or if I go right 2, I go up a quarter. If I go right 1, I go up 1 from the origin point. Right 1 up 1, right 2 up a quarter. I would just go like that. Whoops. And I sort of get the idea here, where if I went halfway, I would have to go up 4 from the line. So I went 1, 2, 3, 4, and I get a nice smooth graph that looks, that doesn't jump like that. That goes straight, and a graph that looks like that. Okay. With the reciprocal function, oh, I forgot to put a graph here. With the reciprocal function, right, we're gonna go left 2, down 1. So if I were gonna draw a nice quick graph, I would go left 2, down 1. That would be my graph, and this is just the parent reciprocal function, so it would look something like that. Okay? Don't want to go too crazy with that one. I didn't make a nice graph for that. Now, those are the easy ones. Okay? So if you have something that looks like one of these two, you can graph them with transformations. However, most of the functions that you are going to graph are not going to be like that. So rational functions that are not transformations are graphed using the following procedure. The following strategy can be used to graph f of x is equal to p of x over q of x, where p and q are polynomial functions with no common factors. So make sure you take the common factors out first if they are any. And there are 7 steps to this. First, determine whether the graph has symmetry. Because if it has symmetry, you only need to graph half of it, and then you flip it over, either over the y-axis or over the origin. So determine whether it's even y-axis symmetry or odd to have origin symmetry. So how do you do that? You plug in negative x, and you see if you get your original function, or you see if you get the opposite. Find the y-intercept, if there is one, doesn't have to be, by evaluating f of 0. Okay, good first step. Next, find the x-intercepts by setting the numerator equal to 0. So the denominator gives us places where the graph is undefined, and we'll talk about that in a second. But if I set the numerator equal to 0, I figure out all the places where it crosses the x-axis. Next, we are going to find the vertical asymptotes by setting q of x is equal to 0. We are then going to find the horizontal asymptotes by using the rule for determining horizontal asymptotes of a rational function by comparing the degree of the top and the bottom. Then you're going to have to plot some points between and beyond each x-intercept and each vertical asymptote. Then we can use the information obtained to graph the function between and beyond the vertical asymptotes, remembering that graphs shoot straight up or straight down, as they get closer and closer to a vertical asymptote, and the ends of the graph will always get closer and closer to a horizontal asymptote. Okay, so let's try one. Okay, so step one, determine symmetry. So we're going to plug in negative x. So that turns into negative 2x minus 1 over negative x minus 1. Okay. When I factor out, or if I factor out a negative to this, I would get negative 2x plus 1 over a negative x plus 1. Those cancel, but these two are not the same. They are not, everything is not completely opposite, right? These two are opposite, but these two are the same. Okay, so this has no symmetry. So none. All right, well, not helpful, but good to know. Next, let's find the y-intercept. So we're going to find f of 0. So that turns into 2 times 0 minus 1 over 0 minus 1, which is negative 1 over negative 1, which is 1. Okay, that's nice. 1 point done. Okay, so f of 0 is equal to 1. Next, find the x-intercepts. In order to find the x-intercept, you take the numerator and you set it equal to 0. So we have 2x is equal to 1, x is equal to 1 half. Okay, so the graph passes through the x-axis because this particular 0, 1 half, only happens one time. So this graph is going to go through that point once. Okay. Step 4 is to find the vertical asymptotes. So to find the vertical asymptotes, I'm now going to set the denominator equal to 0. So x minus 1 is equal to 0, so x is equal to 1. So that means this graph at 1 has a vertical asymptote. So that means that I can put a dotted line on this function. Okay. Step 5 is going to be to find the horizontal asymptotes. Well, if I look at this function, right, notice the degrees are the same. So we take the two coefficients divided by each other, 2 over 1, which equals to 1. So that means, which equals to 2, sorry. That means that this graph has a horizontal asymptote at 2. Draw that in there. Okay, so what that tells me now is that this graph must be closer and closer. This graph, as I go closer and closer to this vertical asymptote, the graph is going to go straight up or straight down, and it looks like it's going to go straight down on the left side and probably up on the right side because I kind of know how these things work. The graph is also, as you get to the ends of the function, is going to get closer and closer to the horizontal asymptote. So step 6 is the step that is not fun. So to rewrite my function, we have 2x minus 1 over x minus 1. I'm going to need to pick some points. Okay, so I need to pick some points that will help me get a good idea about what this graph actually looks like. Okay, and the points I pick should kind of make sense. So I have this coordinate right here. I have this coordinate right here. Let's see what happens on the left side here. Let's plug in f of negative 1. So I plug in f of negative 1. I plug negative 1 in both of those places. I get negative 3 over 2. Okay, so that means that that goes right there. I could keep this going and plug in f of negative 2. not negative 3 over 2, positive 3 over 2, sorry. Plug in negative 2, and that gives positive 5 over 3, which is even closer to 2. Right? This is 1.5. This is right there. And now I can kind of see what the left side of this function looks like because I know it's going to get closer and closer and closer to 2 there. And as I turn around and go down, it's going to get closer and closer to the vertical asymptote there without crossing. Okay, well, now I can't plug in 1 because that's my vertical asymptote and it would give me something that's undefined. But I can plug in 2. So f of 2, when I plug 2 into this function, becomes 4 minus 1 over 1, which is 3. And let's just do one more real quick. F of 4 gives me 7 over 3. And you're going to get a lot of fractions when we graph these things. So f of 2 gave me 3. And f of 4 gave me 7 over 3, which is 2.3. So 2.3 right there. Okay? And I could plug in more points, but I don't really have to because I know what's going to happen is as the graph approaches the vertical asymptote, it's going to go straight up to infinity because I can see the trend here of this graph swooping back up this way. And it's going to go kind of like that and flatten off and approach 2. So the limit of this function as x approaches infinity is 2, as well as x approaches negative infinity is 2. And there's my graph with my 7-step process. Okay. Let's jump right to the next one. Okay. So first, define symmetry. Plug in f of negative x. And that gives me a negative squared turns positive over negative squared turns positive. Good. These two are exactly the same. This is very nice because now I only have to graph half of it and flip it over. Okay. Step 2, y-intercept. Plug in 0. When I plug in 0, I get 0 over negative 4, which is 0. Good. So the graph passes through the origin. Step 3, x-intercepts. Well, set the x-axis equal to, or sorry, set the denominator, or the step 3, x-intercepts. So we're going to set the numerator equal to 0. I was thinking about asymptotes. Okay, we'll do that next. Divide out 3, we get x is equal to 0. Okay, which is kind of pretty clear right there since the graph passes through the origin. All right, here's the interesting part. Set the denominator equal to 0, and we get that x is equal to plus or minus 2, which means that this function has 2 vertical asymptotes at 2 and at negative 2. Okay, so we're going to have basically 3 regions of this graph. We're going to have stuff that happens on the left. We're going to have stuff that happens in between the 2 asymptotes, and we're going to have stuff that happens on the right. Okay. Step 5, find the horizontal asymptote. Well, we have a 2 over it. We have x squared over x squared, which means that y is going to be equal to 3 over 1, which is 3. Okay. Which means my horizontal asymptote is 3. So we got a lot of stuff going on this graph already, okay, before we even start plotting points, okay? And again, this is the part that takes the longest. This is kind of, what we've done so far is just kind of the setup, Okay. This is helpful because now we only have to graph half of it. This is helpful because now we at least know what's happening at the on the y-axis, what the y-intercept is. We should always find the x-intercepts and always find the two sets of asymptotes, the vertical and the horizontal asymptotes. But this is all set up to guide us through the rest of the problem, which is to pick points. So f of x was equal to my function 3x squared over x squared minus 4. Okay. So now I'm going to start plugging in points. Okay. Well, let's start. You can start in whichever section you want. Let's start in the middle because I already have the origin point right here. Okay. So let's plug in f of 1. So if I plug 1 into this function, right, 1 squared, that's going to be 3. 1 minus 4 is negative 3. That's going to be negative 1. Which means that the graph goes like this. And because of step 1, because that I know it is even, it reflects over the y-axis. Now, that's kind of enough information for me to graph this middle section because I know that the graph has to get closer and closer to either negative infinity or positive infinity as I approach a vertical asymptote. So the graph is going to look kind of like this. And think of in between vertical lines, in between the vertical asymptotes, think of it as its own little picture. Okay, so now we have the middle part. Let's do the right, and because this is even, we only have to do one of them because the right will give me the left. I don't want to do that because that's undefined. That's my asymptote. So let's plug in 3. If I plug in 3 into this function, I get 9 times 3 divided by 9 minus 4. So that's 27 over 5, okay, which is about 5.4. Okay. So at 3, this function is about 5.4. Okay, which means that at negative 3, this function is about 5.4 as well. Well, that's not enough information, so I'm going to need probably one more point, f of 4. Plug that in. That's 16 times 3 divided by 16 minus 4, which is going to be 4. Okay? So at 4, this function is equal to 4. Okay? Now if I use what I know, that as this function goes to the right, it's going to get closer and closer and closer to 3. And as this function gets closer and closer to the vertical asymptote, it's going to either go straight up or straight down. In this case, I can see that it's going to be going up. Now I have enough information to finish this graph because I can make it look like that. And like that. And there's my graph. Okay, so you will absolutely need to pick a few points in between each of your vertical asymptotes to get an idea of what the picture looks like. And these two sides do not always have to match, right? They just happen to match because this happened to be an even function. They don't have to. Okay? In fact, well, no. We'll look at one that it doesn't match later. Okay, this one's kind of easy. Determine symmetry. Step 1 is find symmetry. That's even, that's even. So if I plug a negative there and a negative there, it turns into the same function. So this is even. Step 2 is to find the y-intercept, f of 0. Plugging in f of 0 there gives me 0. Okay. Find the x-intercept. So we set the top equal to 0, which is 0. Find the vertical asymptotes. There are none because that has no real solutions. Find the horizontal asymptotes, but because this is 2 bigger than this, there is no horizontal asymptote. So the only thing left is to plot points. Okay, and then use what I know about even functions to help me. Okay, and when I do that, I have this point already, right? If I plug 1 into this function, I get 1/2. If I plug 2 into this function, I get 16/5, which is about 3.2. So that's 1, 2, 3, and a little bit. And because this is an even function, I can reflect those. Okay? And then I could keep going if I wanted to. In fact, if I plug 3 into this function, let's plug 3 in. Let's see what happens. F of 3 turns into 3 to the 4th power. That's 81 over 9 plus 1. So that's 10. So that's 8.1. So 3, 1, 2, 3, 4, 5, 6, 7, 8, and a little bit. And that's kind of enough information to graph this. In fact, it looks kind of like a parabola. Okay? And in fact, notice how the degree of the top is 2 bigger than the degree of the bottom, which means that this does have some sort of other asymptote going on, and because this is 2 bigger, it's going to be shaped like something that looks like x squared. So this has a parabolic asymptote as opposed to a horizontal asymptote. Which leads us to talking about slant asymptotes. Okay, so there are other asymptotes besides vertical and horizontal. Okay, one such example is a slant asymptote. So if you examine the graph of x squared plus 1 over x squared over x minus 1, and here's the picture of that graph. Here's the whole picture. Note that the degree of the numerator is 2, x squared, and is greater than the degree of the denominator 1. Thus, the graph has no horizontal asymptote. But it does have a slant asymptote, and I can figure out the equation of that slant asymptote so that I can draw it on the graph. Okay? So, the graph of a rational function has a slant asymptote, a linear asymptote, right? That's what this means. A linear asymptote if the degree of the numerator is 1 more than the degree of the denominator. We saw in this one that the degree is 2 bigger, so it had a different type of asymptote, a parabola. If it was 3 bigger, it would be a cubic. 4 bigger, it would be a quartic, okay? So we're going to focus, however, on just 1 bigger, okay? So these linear asymptotes called slant asymptotes. If the degree of a denominator is 1 more than the degree of the numerator. The equation of the slant asymptote can be found by division. So divide x minus 1 into x squared plus 1. And hopefully you remember that I can do this because it's a linear factor. I can do this with synthetic division. Don't forget to put the 0 for the missing term, right? X squared, x, 1. Bring down the 1, multiply, add, multiply, add. Okay? We get a remainder, which makes sense because these two are not divisible, but it doesn't matter because all we now have to look at is these terms right here, which, of course, when I change that back to a polynomial, is x plus 1. And so observe that when I divide this, I get x plus 1 plus 2 over x minus 1, right? That's my remainder. That's the equation of the slant asymptote, okay? The result that you get from division, not counting the remainder. Okay. This works because as the absolute value of x gets bigger and bigger and bigger and bigger as it approaches infinity, the value of this goes pretty much to 0. Thus, when the absolute value of x is large, the function is very close to x plus 1 plus 0. This means that as x approaches infinity, or as x approaches negative infinity, the graph gets closer and closer and closer to the line whose equation is y is equal to x plus 1. The line y is equal to x plus 1 is thus a slant asymptote of the graph. So in general, if f of x is equal to p of x over q of x, and p and q have no common factors, the degree of p is 1 greater than the degree of q, you can find the slant asymptote by dividing q into p and ignoring the remainder. So find the slant asymptote here. So remember, we're going to use synthetic division. So we use 3 because we have x minus 3, so x is equal to 3. I don't have to skip any coefficients, so that's 1, negative 4, negative 5. Bring down the 1, multiply, add, multiply, and I don't even have to worry about the negative 8. So the equation of my slant asymptote is x minus 1. And if I look at the graph, I can see that my graph looks something weirdly. I have my vertical asymptote at 3, and I have my slant asymptote at x minus 1, which I should kind of know how to draw. Okay, right? Y-intercept, slope. And then I could go about plotting the rest of these points. And what you should know is that the graph will never cross the vertical axis, or the vertical asymptote, and the ends of the graph will get closer and closer and closer and closer to the slant asymptote. These two are getting closer and closer, as are these two. These, right, the middle of the graph is going to either approach infinity or negative infinity. Okay? So let's do a checkpoint problem. Find the slant asymptote here. So we're going to do the same thing, 2. So we go 2, negative 5, 7, bring down the 2, and that's pretty much all I need. I could keep going with this to get my remainder, but it doesn't really help me. My equation of my slant asymptote is 2x minus 1. This graph has a vertical asymptote at 2. It has a slant asymptote at 2x minus 1. Okay. Let's do some applications. So there are numerous examples of asymptotic behavior in functions that model real-world phenomena. Let's consider a few of them very quickly. An example from the business world is a cost function. For a business is the sum of its fixed costs and variable costs. So this never changes. This changes per unit. The average cost per unit for a company to produce X units is the sum of the fixed and variable costs divided by the number of units, right? That's how you find an average. Take everything and divide it by the number of things you know, if you're producing 30 things, take the cost, divide by 30. That's how much each unit costs. The average cost function happens to be a rational function that is denoted by C bar. C with a bar over the top. Usually that's how we represent average, right? X bar is the average. Okay, so in this case, we're going to use C bar. Okay, let's try it. We didn't go over the opener, but if you make a robotic exoskeleton, suppose a company that manufactures this invention has a fixed monthly cost of $1 million and that it costs $5,000 to produce each robotic system. So write a cost function of producing X robotic systems. So C of X would be equal to the fixed cost, $1 million, plus 5,000 X. That's it. Okay. Write the average cost. So we would take this and say 1,000,000 plus 5,000 x over x. And of course, you should write this the other way, right? 5,000 x plus 1,000,000 over x to keep it in standard form. Okay. Find and interpret C average of 1,000, C average of 10,000, C average of 100,000. Well, now we're just plugging stuff in. Okay. So if we take C bar of x, or C bar of 1,000, we just plug 1,000 into my function right here. And I get 5,000 times 1,000 plus 1,000,000 over 1,000, which would give me 6,000. Okay. I'm not going to write the other two out, but C bar of 10,000 gives me, and you can calculate this if you want, 5,100. And C bar of 100,000 gives me 5,010. Okay. And you should see that if I look at this function right here, it does have a horizontal asymptote. It has a horizontal asymptote at 5,000. So the more I produce, okay, so the horizontal asymptote is 5,000. Okay, the more I produce of this thing, the closer and closer and closer it is going to be getting to 5,000. So what is the horizontal asymptote? I think we answered that. Describe what this represents. It means the more you produce, the better, the more savings you will have, and eventually you can get the cost down to around 5,000. So if you only produce a few, they become very expensive. And as you produce more, you can get it down to, you can get the average cost down. You can sort of spread this $1 million fixed cost for research or whatever over more units that you produce. And this is kind of true with a lot of different companies who are trying, or a lot of different situations where the company trying to make something is you get cost savings at scale, right? You can spread your research over the cost of all of the units as opposed to a few. Okay. Another type of problem we can look at is uniform motion. So if an object moves at an average velocity v, the distance s covered in time t is given by the formula s is equal to v times t, velocity times time. So distance equals velocity times time. Objects that move in accordance with this formula are said to be in uniform motion. In the next example, we will use a rational function to model time in uniform motion. Solving the uniform motion for the formula for t, we obtain that time is equal to s distance over velocity. Kind of makes sense. Thus, time is the quotient of distance and average velocity. Okay. So a commuter truck drove to work a distance of 40 miles and then returned again on the same route. The average velocity on the return trip was 30 miles an hour faster than the average velocity on the outgoing trip. Express the total time required to complete the round trip t as a function of the average velocity on the outgoing trip. So my variable is going to be x is average velocity. Okay, so x plus 30 would be the return trip velocity. All right, because we're going 30 miles per hour faster. Okay, so if I want to make the total time function, I would say t of x equals, well, the total time it takes is going to be time it takes to get there plus the time it takes to get back. So we're going to go 40 miles divided by my velocity, okay, plus probably going to be the same amount back, 40 miles over x plus 30. And there is my function. Now, of course, we should not leave it like that. We should make it a nice rational function, which means that in order to add these two together, I'm going to need a common denominator, which is going to be x times x plus 30, which gives me 40 times x plus 30 plus 40 times x, which then gives me 40x and 40x, that's 80x plus 1200 over x squared plus 30x. Okay? And if I wanted to graph this function, I can. But the question just says, write the function. So here's the function. Okay, so this was a long video, a lot covered. Take a look at MathXL for problems. This was 2-6 rational functions and their graphs.